I'm Dr. Anand. I'll be speaking about meta-analysis, a little bit about how to perform it, and then what are the advantages and disadvantages, or what it tells and what it does not. So we started doing the meta-analysis around 2020. We have around 6 to 7 meta-analysis thanks to Dr. Rupjyoti sir. He was the initial motivation for us to start meta-analysis. There are different meta-analysis and systematic review, narrative reviews. Everything is different. Actually, not everything is not same. Why to do meta-analysis? Who can do it? What is actually required? How to search? That is the major problem with everybody. Advantages and disadvantages. There are 3 types. Narrative review, where we just write some. It's basically author-based. It is biased. Usually, it is selective and prone. We take some articles from the whichever we like, and then we put out a review that is called as narrative review. Systematic, then you have to try and write out which are the search engines you search. Then you make a review. It should be balanced. It is usually considered as balanced with pros and cons of what you have found. And meta-analysis is the statistical process of analyzing and combining all the data. It is called as meta-analysis. Why should we do meta-analysis? There are several studies. Each study will have a different individual characteristics. The inclusion criteria are different. But we combine everything and give a good qualitative and quantitative result, and it becomes a meta-analysis. It is considered as the highest evidence of scientific evidence. The lowest one is case reports, case series, case control studies, cohort studies. RCTs also are very good, but meta-analysis may sometimes give a result which is opposite of what is found in RCT. It is one major drawback of meta-analysis, because there will be combination of RCTs as well as retrospective and case control studies in meta-analysis. But these are the meta-analysis considered strongest. Even if you're forming guidelines, they take from RCTs and meta-analysis the data which has been there, that will be considered as a guideline. In meta-analysis, the effect size of each study will be computed and put together along with the p-value. Whether it is significant or not significant, that has to be mentioned and discussed as well. This, I feel, is the best meta-analysis in hepatology. This was a simple meta-analysis on albumin infusions for prevention of paracentesis-induced circulatory dysfunction. Basically, we try to remove water from the tummy. They said that giving albumin will prevent complications by which happen when you remove this water. This is the only meta-analysis published in 2011, cited 400 times, part of every guideline, practiced everywhere. Every patient who undergoes removal of water, that is ascitic tapping, will be given injections of albumin based on this study. That is the best thing about meta-analysis. You do a very good meta-analysis if the question is relevant, the answers are relevant, then it can be practice changing as well. So what is required? We need to frame a question. It should be timely and clinically relevant. Something which has been done many times is redundant. It won't be useful for any of the clinicians, nor the manuscript reviewers will not be very interested if it is not unique. And usually the most important thing is novelty. It should not have been done. If it is done and again you do it again, then it will not be relevant. And the questions which you want will be usually from the clinical practice, for the clinicians especially. From your clinical practice, there will be few studies, then you combine together and perform a systematic review and meta-analysis to find a relevant answer. That can be very important for the clinicians, for the journals, and for the citation of the article as well. There are 4 components, that is PICO, population which you want to study, intervention which you want to study, comparison group, and the outcomes. It should be clear. The outcomes should be clear, and it should be registered on a website which is called as Prospero. When you do a meta-analysis, prepare your PICO accordingly, then get it registered on the Prospero website. This is the UK-based website. There are multiple of them, but this is considered the best, Prospero. It is freely available. Just make a login account and put the details what you want to test in this meta-analysis and why you're doing it. Because whenever you go for big journals, they go back to your Prospero account, check what you have written there and whether you have mentioned the same objectives there and in the manuscript as well. So this is important to update your Prospero account and update the findings which you have found, and you have to also mention that the article has been published or not. We may also find if there are individuals who are doing the similar kind of research, it will be found on this website. You just go and search for relevant key terms, and then you can find that it is already been done, and there is no use that you again do the same thing. Also, you should be pretty fast. Register it, get it done immediately within 1 week. These are the minimum data set required for registering on the Prospero website. basically the research question, the search strategy, how we'll be using, what are the engines, PubMed, or what do you say? There are multiple of them. Scopus. If Scopus is available, then it has usually good MS. All of them have very good. You can also get the abstract from all those search engines, but from PubMed only the relevant published research will be found. Who are the whom we will be collaborating with? If there is anyone helping, everything has to put out there clearly, and then it is usually done. It's very simple actually. It hardly takes 20 minutes. Who can do it? I feel both can do it, clinicians and biostatisticians. But usually clinicians, they know about the disease and the clinical outcomes will be more well defined, but difficulty with statistics. So we need a help of biostatistician who is strong about statistics, but he may find a little difficulty in analyzing and writing about the discussion. So we need a team to perform meta-analysis. It cannot be done by a single individual. You need a team because data has to be retrieved. There is a lot of data in each study. Everything has to be taken out. The gender, age, what is the patient population, what is his inclusion characteristics, what are the excluded characteristics, number of patients, everything has to be taken out. That cannot be done by a single individual if you are doing a large meta-analysis. There are softwares available. Simple comprehensive meta-analysis is the simplest. You just need to put in the variables. It does everything by itself. The only thing is it costs around $400 per annum. You can use it multiple times. Ravman is very good. R, SAS, Stata, Meta, Excel, all these softwares are available to do a meta-analysis. I use comprehensive meta-analysis because most of the job is done by the software itself. You just need to put the correct values. There are separate checklists. RISMA is for RCTs. MOOS is for observational studies. If you are doing any of the observational studies and you want to report the age or whatever you want, derangement in the LFT in a patient with COVID-19, which is what we done in the first meta-analysis. MOOS guidelines, everything is written over there. What has to be written in introduction, what has to be written in abstract, what has to be written in method. Everything is there in these guidelines. How to prepare a Prisma chart. You just need not bother anything. Just follow that. Your article is most likely to get accepted. The most commonly used, there are several of them: search engines, PubMed, MBAS. These are all Cochrane Library, Google Scholar. But you have to mention what you have searched. PubMed is freely available, very easy to do it. Google search is hand search. Most of the meta-analysis are done on these two itself. But you have to mention that PubMed was used for these criteria, and Google search was also done to find out any relevant recent articles. PubMed searching is what actually most important. The simplest way is go to PubMed, click the advanced, where you will get the next column, that is mesh terms. From mesh terms, you need to know what are the terms which you are trying to assess. For acute liver failure per se, if you say that it doesn't have acute liver failure, it contains fulminant hepatic failure. So there is also a website where you can find which are the terms which are there for the medical terms. So mesh terms is a website. You go there and check what is your relevant search strategy the keyword which is required for you. Then you come back to, you build a search builder in the PubMed and then just write search. Then you will get these articles for COVID-19 and vaccines. This is a pretty long back. There are only 13 articles. This can be directly again taken to your EndNote, and then the search strategy is almost complete. This is the most difficult part, but this will help you in building your Prisma chart. Once it is done, then almost all the meta-analysis itself is completed. So this is how it comes to EndNote. This is the EndNote software where you get all the details which have been selected. You need to also download how you did this search strategy and also mention and give it to the manuscript. You have to mention it in the appendix that these were the terms which I used and these are the results I got from this. So COVID-19 and vaccines were 4,000 at that time, and only on COVID-19 and vaccines and liver. Post this, we did our COVID-19 vaccine effect on liver disease, which also got published. So this must thing search strategy, you should be clear. Find out what is the term you want to search on mesh terms. Put it in PubMed, select the date as well. Then you can, your almost Prisma chart is completed. I usually prefer writing it in a book, why I excluded this article, what is the reason. And PubMed also has that once you click it, the color turns and it's easy to identify which you have already read and which you have not read. Just save the articles which have been recorded. Make a folder in EndNote. If there is a software called EndNote, which is for citation. Just make a folder on that and keep on adding excluded, included, excluded, excluded. Then search that it is done, Prisma flowchart is done. The data which has been taken out from these articles, make a Excel sheet, fill out all this. One individual cannot do it. I usually search and all the articles and give it to my two of my friends. They fill the tables and give it back to me. I cross check and then do the meta-analysis. That's very easy if you have a team and you can do a meta-analysis within 1 week. And take the data, put it in the software. This is the comprehensive meta-analysis software. You just need to identify what you want to report, odds ratio, risk ratio. That's again a different class, but I'm just telling about the basics how to do a meta-analysis. Then once you insert them, then you get a result, and along with the forest plot, everything is there in this software. You just need to copy and finish the manuscript. So what do meta-analysis actually tell us? It usually consists of large data. There might be, we recently published one of the articles on liver cancer. There are almost nearly 47 articles published already within a span of 1 to 2 years on the utility of this drug in the real world evidence. So almost 5,400 patients. Every center has 100 patient, and cumulatively we found 5,400 patients. So almost more than 5,000 patients in that. That has been cited more than 2,240 times and has been part of the guidelines. So the methodology is clear. If your objectives are clear, then most of the time the meta-analysis has several advantages. It combines all the relevant data and gives for a given research issue, you can develop a hypothesis. Once for individually, your statistical validity, which enables it to generalize its findings, use accurate evidence by assessing the trends in several pieces of research. Helps researchers go through enormous amounts of sometimes complicated research. Once you do a meta-analysis, you are usually thorough with that subject, so much thorough that you can give presentation anywhere actually. Okay, that can also be a part of good guidelines. And for personally, it improves your statistical knowledge, critical thinking, whether you have to give balanced review. You cannot just say that yes, this drug is good, this drug is bad. You also have to think whether it was taken from a particular, when you did the COVID study, most of the studies from China reported that the mortality is less than 10%. But when we did the meta-analysis, we found that when the mortality was assessed as per country, USA had 35% and other countries had 20%, but China had less than 10%. That was one unique finding of that meta-analysis. So you have to do subgroup analysis and then find out whether it is right or not. You also get the ideas about what is lacking in the literature and how to prepare a design for the next study. And you can also publish in big journals. There is no doubt in that. Disadvantages of it is it's very time consuming. It requires lots of time. It's rigorous, complex statistical techniques and appropriate abilities are necessary for it. There are also books for it. If you read the books, you get a clear cut, very small books. Once or twice, you will be usually thorough with this meta-analysis performance. You need knowledge about software, how to use it. There are also YouTube videos about it, how to use comprehensive meta-analysis, how to use R, how to use Revman. And it's not appropriate approach for all types of research. There might be I recently got an article to review 30 case reports which have been put together and made a meta-analysis. It is not a right way. Just a small group of 30 patients making meta-analysis will not make any sense. You need to have good number of decent sample size, good number of at least 4 to 5 articles are required to make a meta-analysis. It is also called a gigo effect. You just take garbage somewhere and put it inside, you get something outside. It is garbage in, garbage out. That's the major problem with meta-analysis. Your research question should be relevant to the time, your research questions, your research objective should be very clear, then it has some value. And you should also do some primary searching before you start a meta-analysis. Yes, there are few articles which are relevant, but there is no meta-analysis. Like recently, there was one of the articles on albumin infusions in hyponatremia. There is no data to support it, hardly few articles, and a meta-analysis was done, and which was obviously could not be taken because there is no baseline, there is no data itself. So primary studies, if there is no data, then meta-analysis will not carry any weightage. At least 4 studies are required. Even the software doesn't do any meta-analysis if you have less than 4 studies. 4 or 3, I think 4 is adequate numbers. But if you have more than 10 to 15 publications, they usually bigger journals take some interest in looking at the meta-analysis. There are 2 heterogeneous. As I said, for COVID, some patients are from Asia, some from US, some from other countries. They The inclusion criteria are different, the exclusion criteria are different. You have to match all those things and also discuss about the heterogeneity, what you have found in this meta-analysis. So this is a disadvantage, but if you actually take care of that, do a sensitivity analysis, do a subgroup analysis, then it may be worthwhile to do a meta-analysis. You also, when you are reading a meta-analysis, read about the discussion part. Don't just read the results that a drug, this is very useful. But you also read that there is subgroup analysis. What does the discussion say? Is this biased? Because most of the RCTs are public funded RCTs, company funded RCTs, sometimes may introduce bias into this performance of the studies, RCTs per se. They also look for publication bias, especially, which is very important for RCTs. And not all patients are similar. Inclusion criteria can be different and deals with main effects. There will not be subgroup. You just have that this drug, yes, there has positive effect. Yes, no, yes, no, yes, no. There will be no other outcomes unless you have taken care of everything and mentioned there. You can also do a moderator effect on the comprehensive meta-analysis by like age and gender. Then say that this drug effects probably has more better efficacy in males than females. This can be overcome, but these are all the major disadvantages. I must thank Dr. P.N. Rao because he was the one initially in 2018-19 we were a little depressed that none of the publications are getting accepted. He gave me a book that you read this and start doing meta-analysis. Dr. Roop Jyoti was very instrumental in doing my first few meta-analysis. And this is the team who actually helped me with doing a meta-analysis. Thank you. Any questions?
Any questions, or shall we do the questions later on after your presentation?
Okay.
Then we'll have a better pool of questions.
Good afternoon, all. In this session, I am going to talk on the right statistical test that should be used for the right kind of data. So what are the various statistical tests that we come across in our day-to-day research works, and what kind of statistical data that we collect, and what kind of statistical tests that we should apply for such kind of data. First of all, why should a researcher attempt a statistical analysis? Why a researcher should attempt a statistical analysis? We collect the data, look at the data whether it follows normal distribution or not. Are there any outliers? If there are any outliers, remove those outliers, and then try to see what kind of statistical test should be applied for that, and then get the inference. So if you don't apply statistical analysis and if you just draw conclusions based on your 30 years, 40 years clinician experience, that will some not work out. Sometimes it doesn't work out. So you have to apply appropriate statistical tests, because we study a small group of people from the large population, and then based on the studying this small group of people, we arrive at a conclusion to the entire population. Therefore, we should be very careful in applying our appropriate statistical test. Based on the test results, we conclude our conclusions to the entire population. So statistical analysis is a methodology which is something about a large population is discovered on the basis of observing a small group of or sample from that population. For example, there is one drug A which is gold standard that is already there in the market. You invented a new drug which is drug B which you wanted to test on the sample. So you draw this small sample based on your randomized control trial, and then study those, investigate those small samples, and experiment drug A and drug B to both the groups, and then see whether the difference that you found between those drug A and drug B has occurred by chance alone, or is it because of the true effect of the treatment. So that is where you apply the appropriate statistical test, and then see whether the difference that you found between drug A and drug B has been occurred by chance alone, or is it because of the true effect of the treatment. So if it is not by chance alone and it is by true effect of the treatment that is you found based on the appropriate statistical test, then that new drug will be released to the market in place of gold standard which is there already in the market. So that new drug now will be applied to the generalizable to the entire population from all those set of patients who are suffering from the disease. So as process, while we collect our data, in the medical research, there are two kinds of data that you can collect as part of your research. One is primary data, other one is secondary data. What is primary data? Primary data is collected by an investigator or an organization for his or her own use from the primary sources. So what are the various methods of collecting the primary data? Direct personal observation. What does that mean? Direct personal observation means when you go to a village for a information collection. So you look at the household, what kind of household it is. It is a kacha house or pakka house, what kind of it is, whether the household has a drinking water facility or sanitation facility, etc. So all those information you observe and then collect the data. That is direct personal observation. And by using the questionnaires, you send the questionnaires by email or post and ask the respondents to fill the questionnaire and send back. So that way, if you collect the data, that is by using questionnaires, collecting the data, primary data, and by using the personal interviews. So as part of investigation, you design a questionnaire and ask the patient, such as demographic details, personal details, and smoking history, if they have smoking, any clinical history, so diabetes, presence of diabetes, hypertension, all those information if you collect from the questionnaire, that is by using the personal interviews. All the census and sample surveys are sources of primary data. So all these data you collect and then investigate and do the analysis and draw the conclusions and generalize those findings to the entire population. On the other hand, you have secondary data. It is collected by again an investigator, and the various sources of secondary data are published reports. There are official published reports will be there. Journal and newspaper, you collect the data, and local government publication, you collect the data. University or research institutes publication, you collect that. All these data, when you collect from these nothing but secondary data. So whatever the data that you collect as part of your medical research, those data can be broadly classified under two headings. One is qualitative data, other one is quantitative data. So qualitative data is qualitative by name itself, you cannot quantify it in terms of some unit. Whereas quantitative data, you can quantify it in terms of grams, weight, height, those kind of data can be quantified. Qualitative data can again be classified under two headings, nominal and ordinal data. Nominal data, there is no any order involved in it, like such as gender, male, female, type of drug, place of residence, rural, urban, disease, presence, absent. All these kind of data is called nominal data. So depending upon your data, you have to apply different statistical techniques. So what are those statistical techniques depend on your data that we will see in next slides. And so qualitative data again classified as ordinal data. Ordinal means by name itself, you have some order involved in it, like stage of cancer, severity of pain, mild, moderate, severe. All these kind of data is nothing but ordinal data. So on the other hand, you have quantitative data which can be quantified. Again, it can be classified under two headings. One is discrete, another one is continuous data. What is discrete? Discrete is number of children in a family, number of bacterial colon and plate, all those nothing but discrete data. On the other hand, continuous data is nothing but you quantify the data and take measure the data in a given range. For example, age can take any value ranging from 0 to 100. Similarly, height, weight, volume, and systolic blood pressure, diastolic blood pressure, all those kind of data is nothing but continuous quantitative data. Continuous quantitative data can be again classified under interval scale and ratio scale. So what is interval scale? Interval scale is you have, for example, body temperature in degrees Fahrenheit. So interval scale, sometimes it goes beyond 0. For example, temperature minus 10 degrees, minus 20 degrees. So beyond 0 it can go. Whereas the ratio scale, it cannot go beyond 0. And volume, height, weight, length, you cannot say 0 weight. You cannot say. So ratio scales are all those which are greater than 0. So these kind of data, whatever you collect, depending upon the data that you have collected, the type of statistical analysis will vary. So whether it is a quantitative data, whether it is a qualitative data, what kind of data that you have collected as part of your research, your statistical analysis will differ. If it is a continuous data, then such as height, weight, etc., then systolic blood pressure, all those those variables are continuous variables. These continuous variables, if you have collected, then the best way to do is just do the graph bar diagram. So there you will get a histogram. If it looks like a normal distribution, which is bell-shaped curve, so then it is called normal distribution. Then if it is a normally distributed, then you can calculate mean, median, mode, standard deviation, range, percentage, if all those data follows normal distribution. Otherwise, if it doesn't follow normal distribution, it is either right skewed or left skewed, then you have to use median and interquartile range. And if the data is categorical, if not continuous, categorical, then you simply calculate percentages such as percentage male, percentage female, etc. And if data sometimes it is normally distributed or not, you can just calculate 2 multiplied by standard deviation, and it should be less than mean. That is the thumb rule. So 2 multiplied by standard deviation is less than mean, or mean is equal to median is equal to mode. All three are same. Then you can blindly say that the data follows normally distribution. Histogram also it comes like this, what you are seeing in the picture. So it will be bell-shaped curve, and you can use the if the data doesn't follow normal distribution, then you have to transform the data by using suitable transformations, such as by using the log, square it, or cubic, inverse the data, or square root it. So if you do such kind of transformation and then see whether that follows normal distribution or not. So if the data follows normal distribution, then as I said, statistical test differs. You can use parametric test as far as test of significance. If the data doesn't follow normal distribution, even after suitable transformations, then you have to use another test which is called non-parametric test. So parametric test, non-parametric test, what is the difference between these two? Parametric tests are applied when the distribution is normal, and if non-parametric test is applied when the distribution is skewed, as I shown in the picture, it is either right skewed or left skewed. Even after suitable transformation, it is still skewed distribution. Then you have to use non-parametric test. And parametric tests are applicable for quantitative data, whereas non-parametric tests are applicable for qualitative data. And parametric tests are applied when the scale of measurement is metric scale, like interval ratio scale, as I given in example in the previous slide. Then you can use parametric test. Whereas non-parametric tests you can use for nominal and ordinal scales like male, female, disease, yes or no. All those kind of tests you can use non-parametric test. And parametric test use means and standard deviations. Mean is nothing but you calculate. It will be used each and every patient's data will be used in that. So that is why parametric tests are more powerful. Whereas non-parametric tests, you will collapsing the data or you will put them in the groups. Therefore, it will have less power. So parametric test, the most important parametric test that you usually come across is independent sample test, which many of you must have already used, or if not used, the independent sample test is used when you want to compare the difference between two groups. The two groups, when I say they are independent to each other, like male, female, they are independent to each other. So when you have the data mean comparison between two groups, then you go for t-test, and t-test assumes that the data follows normal distribution. Example, is there a cholesterol difference between two groups of patients who are given different treatment options? So if this is the situation, you go for independent sample t-test. Before doing an analysis, you set up a null hypothesis saying that there is no difference between groups. Mean difference is same across the groups. So this is, for example, the data. Changes in cholesterol of adults received by two different treatments. And one is diet, other one is exercise. And cholesterol is measured for both the groups, and then see whether the mean cholesterol is significantly different between those participants who received diet and who received exercise, two kind of modalities, treatment modalities. So this is the formula that we use for independent sample t-test for this kind of data. You compare the difference between take the difference between the means between two groups, as I have already given. Exercise one group, diet is other group. The mean you calculate, mean cholesterol you have calculated, that is x1 and x2 bar. X1 bar, x2 bars are the cholesterol means of those two groups, and then divided by the standard error of the difference. Standard error of the difference is given by SP into square root 1 by n1 plus 1 by n2. N1, N2 are the sample sizes of each group. So the other situation that researcher comes across is same patient measured before and after intervention. So this is called paired data. So for paired set is used when you want to compare the pre versus post differences of the same group. So this also assumes that data follows normal distribution. And for example, the data is collected changes in creatinine pre versus post treatment received by 10 patients. So the creatinine has been measured before the treatment and after the treatment. And then whether is there any significant improvement in the creatinine. So this is the test you use, paired sample t-test, which is given by d bar divided by standard error by standard error, which is given by standard deviation by root 10. So d bar is nothing but you take the differences pre versus post intervention parameter, and then for that difference you calculate the standard deviation, and the n is the sample size in the formula. So take d bar divided by standard error gives the whether is there any significant improvement in the post intervention. So that is where you use a paired sample t-test. When there is a situation where you compare the means between more than two groups, in that situation we go for analysis of variance. So when we want to compare the mean difference between more than two groups, we use the analysis of variance. For example, hemoglobin levels of 3 groups of children fed 3 different diets are given. So if that is the situation of the data that has been collected as part of your research, then if you want to test whether the means of those 3 groups differ significantly, so we use one-way ANOVA. For every parametric test, there is a corresponding non-parametric test. As I explained, for every statistical test, there is a parametric test, there is a non-parametric test depending upon the data that you have collected. So if it is if it is not following normal distribution, sometimes also called Gaussian distribution, then you have to use non-parametric test, and every parametric test has corresponding non-parametric test. So for example, two independent groups, if you are comparing the mean difference between those two groups, then you have to use independent sample t-test if it is normally distributed. Otherwise, the corresponding non-parametric test is Mann-Whitney U test, or it was also called Wilcoxon's rank sum test. If it is a paired data, you are comparing pre versus post intervention, then the parametric test is paired sample t-test if the data follows normal distribution. Otherwise, even after suitable transformation, if the data doesn't follow normal distribution, you have to use non-parametric test, which is Wilcoxon sign rank test. So these tests have been invented by a Pratt Wilcoxon, who is a statistician. And if you have mean comparison between more than two groups, then Kruskal-Wallis test is the corresponding non-parametric test for ANOVA. So for example, if the data doesn't follow normal distribution, then Kruskal-Wallis test should be used for more than two groups comparisons. It works based on the median values for comparison between more than two groups. The other most important test that we usually come across is chi-square test. This is again very important test which most of the researchers they use quite often. The chi-square test is a non-parametric test. This is used to assess the association between two or more categorical variables. For example, smoking, yes or no, and lung cancer, yes or no. So the requirements for this chi-square test, the data should have been collected randomly, and observations must be independent of each other. For example, no matched pairs, and cell count must be greater than 0. So for each cell, you have to have a count which is greater than 0, which can be 2 by 2 cells or 2 by 3 or 3 by 2, whatever. So in that situation, you go for chi-square test. The null hypothesis that the chi-square test uses, there is no association between groups. Like in this case, smoking versus lung cancer. There is no association. That is the null hypothesis we set up. And we apply this statistical test, which is chi-square test is given by summation observable value minus expected value whole square divided by expected value. So that is what the chi-square test is given by. and observed value are the values that you have collected, and expected value you calculate for each cell observed. For each observed value you calculate the expected value. For example, in this case, smoking status versus lung cancer. Smoking is light smoker, moderate smoker, heavy smoker, and the lung cancer, yes or no. So for A, B, C, D, E, F, for each cell you calculate the expected value for this kind of data, and the expected value for A given by A plus B corresponding row total, corresponding column total multiplied by total sample size. So that is how you calculate the expected values, and subtract those expected values from observed values and square in and divided by the expected values. You get the what is called chi-square test value. So in the other example, prenatal care received by the pregnant woman and the survival status of the infant. So less care received and more care received by the people, pregnant women, and their survival status, whether are dead, alive, are given in this example. So the degrees of freedom usually for chi-square test is given by row total minus 1 row total, number of rows minus 1, number of columns minus 1, multiplied by those two will given the degrees of freedom. And then chi-square test value, as I shown in the previous slide, is given by the 5.26 by using that formula 5.26. Whether this value is occurred by chance alone, or is it there was a really less care received pregnant woman has a higher status of dead. So if you want to see that, you will apply the chi-square test and then see whether the chi-square test has occurred by chance alone, or is it there was a real association. So you see the p-value, calculate the p-value, and if it is less than 0.05, then you say that there is a significant association between prenatal care received by mothers and survival status of the infant at 1 month. So the p-value here less than 0.05, therefore there is a significant association, and then you conclude that there is an association between prenatal care received and survival status of the infant. And on the other hand, you have a 2x2 table which is smoking only yes no, and lung cancer. In earlier situation, smoking 3 groups. You have light smoker, moderate, and heavy smoker. In this case, only you have categorized them into smoking yes or no, and lung cancer yes no. So if this is the data, if you have, then you can use the more powerful test, which is called Fisher's exact test, which works out by the formula p-value is given by a plus p factorial, c plus d factorial, and a plus c factorial, b plus c factorial multiplied by all those divided by a factorial, b factorial, c factorial, d factorial, and n factorial. So this is more powerful for 2x2 table. And whatever you get the value, that is the p-value, and if it is less than 0.05, then you say that there is a significant association between lung smoking and lung cancer. And one more important test, what is called McMahon's chi-square test. This is again important. When you have the data measured for 2x2 table, pre-intervention, post-intervention, same patient has been measured pre versus post and categorized into 2x2 table. If this is the case, if you have collected the data, then you have to use McMahon's chi-square test. This is again more powerful, important test, which is given by chi-square test is given by b minus c whole square by b plus c. So these are the various. Another example is for McMahon's chi-square test. Effectiveness of special diet and weight loss exercises in 314 patients were given in the experiment for 6 months duration. So this is the before exercise weight obesity data has been documented from the patient. After exercises 6 months, again post experiment same obesity has been measured, calculated. So obesity has been observed. So pre versus post, is there any difference? That is what is in this data. P-value less than 0.001 means that exercise, weight loss exercise has effect on these 314 patients. Before and after intervention, weight loss was significantly seen. So this is how you use the McMahon's chi-square test in this kind of data. So correlation is again one more important analysis, correlation analysis again, which is most quietly used by the clinicians or researchers. The purpose of studying relationship between two continuous variables is nothing but correlation. What is the purpose of studying relationship? Whether is there any association between height and weight? So if height increases, weight increases, or age increases, systolic blood pressure increases or not. So when you are assessing such kind of purpose of such kind of relationship between two continuous variables, we go for a correlation coefficient. So correlation is usually associated between two groups. Not two groups. Same kind of patients receive before or after intervention from the same patient. From the observations are measured from the same patient twice on two kind of parameters. So if and we see whether those two variables are related or not. So if there is a relationship between those two variables, then that can be used for predictions. So one variable can be used for the prediction of the other variable. So what is the purpose of what are the various methods of studying relationship between two continuous variables? One is scatter diagram. So you just use scatter diagram and then see whether the data fairly follows any kind of positive or negative relationship. If there is a positive relationship, the data on the straight line will be have one variable. The effect of one variable increases the effect of the other variable in the same direction. If it is negative correlation, the effect of one variable affect the other variable in the negative direction. That means one variable increases, other variable decreases. So correlation coefficient is used to measure the strength of relationship between those two variables, which is denoted by R, which ranges between -1 and +1. And this is the formula used for correlation coefficient. And the best way to interpret the correlation coefficient is to calculate the coefficient of determination, which is nothing but R square. R into R is nothing but R square. So that gives us the kind of sense that what is the explained variance on the total variance. That, for example, if R is calculated as 0.9, age and systolic blood pressure, let us say it is 0.9, then 81% is on the changes of systolic blood pressure is alone explained by the age itself. Rest of the variation, 19% variation, is explained by the some other factors. So this is how you interpret the correlation coefficient, by calculating the coefficient of determination. And the different indices for the correlation coefficient for different kind of data that you have collected as part of your research. Pearson product correlation coefficient is used to assess the relationship between two continuous normally distributed variables. And the Spearman's rank correlation coefficient is used to assess the relationship between two continuous variables and at least one which is not normally distributed. And Kendall's rank correlation coefficient is used to assess the relationship between two ordinal variables, or one ordinal variable and one continuous variable. Intra-class correlation coefficient is used to assess the agreement between two continuous variables which are measured on the same scale. So, for example, two clinicians have measured the systolic blood pressure. Whether those two clinicians are correlating, agreeing both each of them, then you use the intra-class correlation coefficient to see if it is close to 1, then both the clinicians are measuring on the same patients with the same exact systolic blood pressure. So that is how you interpret. And the other important analysis is called regression analysis. When there is a correlation between two variables, that means there is a relationship. Then what next? The next is, if that relationship between the two variables, continuous variables, is on the if one variable influences the other variable in the same direction, positive correlation if it is 1.0, or -1.0 if it is negatively correlated, then you can best predict those data by using the regression models. So regression analysis is used for the best predictions. So forecasting, prediction, for all these use regression models. So nowadays, even for stock market, day to day they use the regression models for the forecasting. And if other situations where you use the regression models is testing the IQ affects the income. If the IQ affects the income or not, you can use the regression models. And working of hours affects the working of hours of sleep, that you can use the regression models. Cigarette smoking affects the blood pressure, you can use the regression models. So if you have the data measured Pancreas smoking and occurrence of cataract, then best way to use the regression models to predictions. On the other hand, you have the other important regression model is logistic regression. This is the most important model that we use day to day our clinical research or anywhere, any research. Logistic regression model is used when you have the outcome measured on the binary scale, like yes or no, this is dead, alive. So all the independent variables are either categorical or continuous variables, and this is most frequently used analysis in medical research. And in summary, so whatever I spoke so far, all those I summarized in this slide. If you have two independent groups, then mean comparison, you use the independent sample t-test. If it is a parametric test, non-parametric test, use man-weight u-test. If it is a nominal data, then chi-square test. If the paired data, pre versus post intervention, you have collected the data, then you are comparing the mean difference by using the parametric test, use the paired sample t-test. Otherwise, non-parametric test, Wilcoxon sign rank test. If it is a categorical data, McMahon's chi-square test. More than two independent groups mean comparison when you are doing parametric test is ANOVA. The corresponding non-parametric test, if it data not normally distributed, then critical values test we use. And if you are measuring the relationship between two variables, then Pearson chi-square test is a non-parametric test, and Spearman rank correlation coefficient is a non-parametric test. If the two continuous variables measured on the same individual, then correlation analysis you can use for relationship between, to find the relationship between those two variables. One continuous, other one is a categorical variable, then regression analysis best used for predictions. And if you have an outcome variable is binary yes or no, disease present absent, and other variables are continuous and categorical, then logistic regression analysis is used. You have other important time to event data. You follow over a time period whether any event occurred. In this case, event is interested is death. So patient death alive over a period of time, then you independent or continuous or categorical data. If you have, then cost regression analysis is the best method that you can use for predictions. So thank you for your attention. Any questions?
Thank you, both the speakers. Very beautiful talk. So, any questions and comments?
Yes, we have to. After subgroup analysis, we usually remove them off. On sensitivity analysis, you just take the RCTs or the studies which have high quality, like a prospective observational studies, and we remove those abstracts. But everyone has to know about statistics, all the tests, everything. If you are really interested in research or publication, then statistics is the Achilles heel. Everybody has to know it.
And a few papers, if you don't have access to the full paper, do you rely on the abstract numbers?
We rely on the abstract. We mail the authors. We mail the authors to send the papers, and we give their name. Most in the recent one, I had put 6 authors' name because they gave their data to us.
Any more questions? There should be lots of questions. No, everyone is doing research.
I have one question actually. How to match the population? Because there are something like there are 20 young people who are eating oranges, and they say that oranges is good for health. There are 50 elderly people who are eating apples, and they say that apple is good for health. How to match this population? Matching.
By gender and age, best we can match. SPS. Okay. So usually we can select the sample based on the certain criteria. So that criteria can be either it can be age matched criteria, gender matched criteria, or socio-economic status. By socio-economic status, we can match and then see whether higher socio-economic status has what kind of effect on the drug, and lower socio-economic status.
You exclude all those who are not in the
not in the categories.
That's all.
What kind of studies are we supposed to do meta-analysis? Suppose there are 20 studies which have shown all positive results. Is meta-analysis in that question makes sense?
Does not make sense, sir. If you have any conflicting reports, it is better that you get do a meta-analysis and report it. But if you have good number of 20 articles and you are doing something which is not the primary outcome of those 20 studies, it is something like you wanted to note that effect of albumin on something else, kidney injury, which is not the primary outcome. and you can do meta-analysis.
The data.
Difficult.
Barring the biomarker identification.
Difficult you can do, but
Not-
very difficult. But for clinicians, if you don't have any patients' data, it's a very good way to get public. If you, for the clinicians, if you don't have time to accumulate the data, take care of all the data, AIG, we have lots of data, but it was the initial struggle. That time we used to do meta-analysis.
An article has only a part of the data we require. You can take a part of it, or the data should be the prime point of the paper also.
No, you can.
Like, for example, if there is data on echalacia, including everything, redo poem and like post-Hellers and all that, and we are writing a meta-analysis only on redo poem or post-Hellers or something, we can take only the data.
You can take that data, but for any meta-analysis, it is preferred to state the basic baseline characteristics of these patients. So if you see any meta-analysis, if you want to go into big journals, your methodology has to be very strong, at least 2 pages of good methodology, what you have actually done. And as and when you are doing results, you should also put it in methodology that I have been doing this and this is how I got these results. In results, you always start with baseline characteristics. These are all the patients who had undergone POEM. These were the baseline characteristics. And we all just want to assess this part, but this has to be there.
And these things can be done as sub-analysis. There will be one primary question, and then all the other things that you were saying, part of the study can be sub-analysis. And the other important thing on meta-analysis that I would add is there is something called sensitivity analysis. Suppose one study has a very strong effect. Suppose the odds ratio of one study is 5 and the other studies are below 3 or 2. So there is something called the sensitivity analysis, that because the whole study may be biased by one study of 5, I think. So if you do a sensitivity analysis, you can rule out the biased effect of one particular study. That's another important point.
Best thing about meta-analysis, you need not do anything. Just have a computer and sit in front of it. 1 hour per day will be done with one paper.
So any more questions?
So when there are multiple papers on the same topic, how to decide which one to include and which to
You
exclude
have to
for
include,
meta-analysis?
if you have 3 or 4 objectives, even if the paper states only one of the objective as its outcome, like if you are looking at impact of CRRT on ALF, but the paper does not have anything about that. But there is data of ALF. They have written that these many patients underwent CRRT. That will be part of your baseline characteristics, but will not be part of your outcomes. Impact on mortality will not be there. But all you have to include as many as articles as possible.
Any more questions from the bioinformatics guys there? No?
Big journals look for number of papers as well, 10 to 15 at least. Sample size, even if it is like 100 or 200, but in each group, at least a good.
Published in a decently big journal, but they have just done 20 samples. Another, so I totally would have 10 papers, but my total samples are only 100, 200. Or is that okay, or should I take lesser number of papers but bigger sample
If the
size?
subject is very unique and the studies are very low, 10 with 100 and 200 will do, but if our objective should be very impactful for the journal as well as for the clinicians who are practicing. So initially, if there is no data, like for COVID, you have so many papers, it's very impossible. 100, and we had studied patients from 10 to almost like 1,000. You have to include everybody, but as sir said, you have to do samples based on this. If the 1,000 has more impact, then you do a sensitivity analysis. What they count is actually your research objectives and your clarity in presentation of data. 10 is usually ideal, better to have good impact.
Is it necessary we should process all of the data as raw data, or
Yeah.
are some papers which have already got like some processing, like they've already done some amount of processing and given the data in Excel sheets? So can we use that, or is it advisable that we should take like raw data?
Raw data. For HCC especially, they do individual patient data analysis to overcome all the bias. whatever research has been done, take the data of individual patient and then combine and report it.
Two important component he already said is the bias and the quality of study. For different kind of data, if it's like continuous outcomes or categorical, the quality measures are different. There are different parameters which you can use to, and that should be reported in the meta-analysis. If you read meta-analysis, there will be a section in the result quality of studies, right? And there will be a risk of bias. Again, that will be different based on the type of data or type of outcome. Is it a continuous variable outcome or a categorical? So those are very important. That question that you asked, like number of samples may be low, number of studies are more, those things will come under that quality. So based on that, it could be better, good quality, bad quality. There are many parameters based on the data. So that is important. So those things should be reported. And then another thing is called publication bias. So sometimes usually journals do not report negative studies. There is always a tendency for the interest of the journal, which is wrong. I said already before. So that's why there could be a bias in the some studies. There will be more positive studies or more negative studies. So the publication bias is also important because that can also impact the final implication of the meta-analysis.
Even basic scientists can do meta-analysis if they can help and collaborate with clinicians.
I had a question on the statistics part, sir. So if we have a simple 2 into 2 table, like just like the example that you gave, say smokers versus cancer. So do we do a Fisher's test, chi-square test, or the McNemer chi-square test? Like all of them may be applicable for the kind of data.
Independent groups like smoking versus lung cancer, then chi-square test. If you have the same patient before intervention, after intervention, categorized 2 by 2 table, McLemone's chi-square test only for 2 by 2 table. So Fisher's also only for 2 by 2 table, not more than 2 by 2 table. If you have a smoking light smoker, moderate and heavy smoker and versus lung cancer, then chi-square test only should be used.
Is there something to do with the number of samples in deciding whether chi-square or Fisher's exact?
Fisher's exact test for only 2 by 2 table.
No, I know, but both are 2 by 2, but number of total samples, more than 30, less than 30, is there something? Like if the sample size is very high, we go for more of Fisher. If the sample size is lower,
if sample size is more, then chi-square test will go the best. But because the data follows normal distribution, and if it is normally distributed, then chi-square test would be give approximate. Chi-square test, because if the data follows normally distributed in more than 100 sample, by default data follows normal distribution, then chi-square test will be appropriate.
Two-sided.
Only for 2 by 2 table.
No. Actually, SPSS gives one-sided and two-sided. The
Two-sided.
one-sided usually matches with your chi-square test result.
One-sided is for you have a direction. One drug affects the other drug, surely affects, that is one-sided test. Two-sided test is you have there is no relationship kind of hypothesis you set up. No association between the treatment groups and outcome. So that is two-sided test. Two-sided test p-value is always
questions. Okay. So can you put that slide? There was one slide there, no? Last slide. So I think we, since the statistics things are going good, we should continue this. So what we decided, like we have this whole month we learned about from research misconduct to take care of the data, how to clean the data, present it in an analyzable manner. And then we heard about meta-analysis, how to use the right kind of test. So what is equally important is how you present your data, right? So that's what I think next November we'll do this like all about data presentation. So these are the topics and those are the speakers. They may change this way, that way, but by and large this would be what we are going to do. So that from knowing how to do the analysis, next would be how to present the data in a acceptable format. So thank you. So today we'll stop it here. Again, we'll see you on 2nd November with data visualization, which is art and science. It's not about science only. Okay, thank you. And so ideally, it would be best if the institute can get it with multiple access. I don't have a licensed version. Someone gave me. I don't know about you. So yeah. So I think maybe we can talk to. So if we have a multi-use version for the institute, that would be the best. I know that's what. Yeah. Yeah. So we can talk. Yeah. Thank you.